Welcome! Today we are exploring the repository pattern, a fundamental concept for building clean and maintainable front-end architectures. As shown in this diagram, the primary goal of this pattern is to decouple our business logic, represented here by the UI component, from the complexities of data access. Instead of having our components interact directly with the database or an external API, we introduce a repository as an intermediary layer. This abstraction allows the UI to remain agnostic of where the data originates, whether it is from a local cache, a remote server, or a cloud-based database. By implementing this separation of concerns, we create a codebase that is much easier to test, refactor, and scale.
Direct API calls from UI components often seem like the path of least resistance, but they carry significant hidden costs. As illustrated by the tangled connections between components A through E and the database, bypassing an abstraction layer creates a spaghetti architecture that is inherently fragile. This approach leads to three critical issues. First, it results in tight coupling. The user interface becomes overly dependent on the specific structure of the backend, meaning any change to an API endpoint can cause widespread breakage across the front end. Second, it makes testing significantly harder. Mocking global fetch calls is brittle and complex, adding unnecessary friction to the development lifecycle. Finally, we encounter the problem of inconsistent data. When formatting and transformation logic is duplicated across multiple components, maintaining a single source of truth becomes nearly impossible, often leading to UI discrepancies and maintenance headaches.
The repository pattern serves as an architectural middleman, acting as a critical abstraction layer between our application logic and the underlying data source. As you can see in this diagram, instead of each individual component, from A through E, connecting directly to the database, they all interface through a central repository. This centralizes data access logic and promotes a clean separation of concerns. The primary advantage is that your components remain completely agnostic of the data source's implementation details. Whether the data is coming from a SQL database, a NoSQL store, or an external API, the components do not need to know the technical specifics. By following this pattern, we ensure that our components focus solely on the fact that data is being fetched, while the repository handles the complexities of how that data is actually retrieved. To better understand our system architecture, let's use the mental model of a library. Think of the UI component as a library patron. They simply want a specific book, or in our case, data, and they shouldn't have to worry about the logistics of where it is stored or how it is fetched. The repository acts as the librarian. It provides a clean interface for the patron, knowing exactly where to look, performing any necessary cleanup or formatting, represented here as dusting off the book, and delivering exactly what was requested in a usable format. Finally, we have the API, or database, which represents the library's backend stacks. This area can be messy, complex, and difficult to navigate, containing raw data and intricate relationships. By using the repository pattern, we shield the component from this complexity, ensuring a clean and efficient separation of concerns. This architectural blueprint illustrates the flow of data through three distinct sections of our application: the UI layer, the domain layer, and the data layer. The process begins within the UI layer, where a front-end component, built in a framework like React or Angular, initiates an action, such as calling a getById method. To maintain a clean separation of concerns, this component does not communicate directly with the backend. Instead, it interacts with the domain layer via a repository interface. This interface then triggers the API implementation in the data layer, utilizing tools like Axios or Fetch to perform the actual data retrieval. Once the raw data is returned from the API, it passes back into the domain layer to a mapper function. The role of this mapper is to transform the raw data into the specific model required by the front end. Finally, this processed data is sent back to the UI component, completing the cycle and ensuring that each layer remains independent and manageable. Step 1 focuses on establishing the contract by defining our interfaces. The primary objective at this stage is to define what the system must do, rather than how it achieves it. As you can see in the code example, this file contains zero implementation logic. We first define the user interface to represent our data structure, followed by the user repository interface, which outlines the necessary data operations like fetching or saving users. It is essential to understand that the application relies entirely on this contract, not on a specific API implementation. This decoupling allows us to swap out underlying services without affecting the core application logic, ensuring a more maintainable and testable codebase. In the second step, we focus on the concrete implementation of our repository. Here, the API User Repository class implements the User Repository interface. This is the only location in your entire application where the Axios library is permitted. By isolating our external dependencies within this class, we establish a clean boundary. The getById method demonstrates this principle. It executes the asynchronous call and immediately passes the raw response data to a mapping function. This ensures that the rest of your system works exclusively with domain entities rather than external data structures. If you ever need to switch from Axios to Fetch or another library, this is the only file you will need to modify. Let's discuss what I consider a secret weapon in building robust front-end applications: the mapper. Often, there is a mismatch between the raw data we receive from an API and the clean domain models we want to work with in our code. As the funnel graphic illustrates, we take raw, snake case data from the backend and transform it into consistent camel case objects for our application. In this code example, the map_DTO to domain function serves as a dedicated translation layer. It allows us to perform several critical tasks at once. First, we normalize property names, turning user ID into a simple ID. Second, we can aggregate data, such as combining first name and last name into a single full name field. Finally, we can transform data types, such as converting a status string into a clear isActive Boolean. By centralizing this transformation, we decouple our application's business logic from the specific structure of the backend API. If a backend field name changes, we only need to update the mapper, keeping the rest of our codebase clean and unaffected. Let's examine a common scenario where the backend changes a property name, for example, switching first name to first name. Without a repository pattern, as shown on the left, this minor change ripples through your entire application. Every component that consumes this data breaks, forcing you to perform a risky find and replace across 50 or more files. This process is error-prone and significantly increases technical debt. Conversely, on the right, we see the advantage of implementing a repository with a dedicated mapper. The mapper acts as a protective shield between the external API and your application's internal logic. When the backend structure changes, your components remain completely untouched. You simply update a single line of code within the mapper to reconcile the difference. This architectural choice ensures safety, simplifies maintenance, and keeps your front-end resilient against back-end volatility. In this slide, we're looking at an example of framework integration with React, focusing on how we can maintain a clean separation of concerns. The code demonstrates a user profile component that utilizes a custom hook called useUser. By abstracting the data fetching into this hook, the component itself remains completely agnostic of the underlying implementation details, such as Axios or specific API endpoints. As shown here, the component's primary responsibility is to handle the UI state. It displays a loading indicator while data is being fetched and renders the user's full name once the data is available. This pattern ensures that the UI only receives and reacts to data state, keeping the fetch logic decoupled and making our components much easier to test and maintain. Let's examine how our architecture integrates with the Angular framework. In this code example, we define a user component that needs access to user data. By leveraging Angular's native dependency injection system, we simply declare the user service within the constructor, and the framework handles the instantiation and injection automatically. As shown in the ng-init method, we can then easily retrieve a user by their ID. This approach makes our code highly modular. Because the component depends on an abstraction rather than a concrete implementation, swapping out different repositories for testing or varying data sources is incredibly straightforward. To ensure our unit tests are both instant and reliable, we employ a strategy that separates our production environment from our testing environment. When running in network mode with a real API, performance can be hindered by latency and flakiness. By utilizing a mock API in test mode instead, we achieve results that are both immediate and deterministic. The key to this flexibility is our use of an interface, which allows us to seamlessly swap the live backend for local memory during the testing process, maintaining high velocity and stability in our development pipeline. In this mock implementation, we replace a complex database dependency with a simple array to create a fake database. The mock user repository class implements the user repository interface, ensuring it can be swapped in seamlessly during testing or development. As shown here, the mock.db property holds a set of hard-coded user objects directly in memory. When we call the getByI method, it remains asynchronous to match the signature of a real repository, but it returns results instantly. This avoids network latency and external dependencies by searching the local array instead of a live database. This example demonstrates how Jest and React Testing Library work together to create fast, reliable unit tests. In this scenario, we are testing whether the user profile component correctly displays a user's name. The process begins by creating a mock repository, which allows us to simulate data retrieval without the overhead or unpredictability of a live network request. We then render the component, passing the mock repository as a prop. To complete the test, we use an asynchronous finder to locate the text Alice Johnson and confirm its presence in the document. By leveraging these mocks, the test executes in a mere 12 milliseconds, ensuring our development cycle remains rapid and efficient while maintaining high confidence in our code's behavior. Let's look at the critical differences between making direct API calls from your UI and implementing the repository pattern. When data fetching logic is scattered throughout the UI, it creates an anti-pattern that is difficult to maintain. By adopting the repository pattern, we centralize this logic into a dedicated class, providing a single source of truth. Testing also improves significantly. While direct calls often lead to brittle and slow tests, a repository architecture enables easy, near-instant validation through mocking. Furthermore, refactoring becomes a much safer process, reducing risk because changes are encapsulated. Finally, this approach ensures your application remains decoupled from the backend, allowing your domain logic to stay independent of API changes. Professionalizing your front-end architecture today starts with these essential structural improvements.